Hey folks, today we're going to be talking about top K YouTube videos. This is a really popular family of problems. YouTube videos just being one version. We hear this about Spotify and others that gets asked across a wide variety of companies. I would call it a classic problem that has a lot of different variants. If you've been following this channel for long, you might have seen a previous video about this. Got some feedback that video was harder to follow, so we're going to make this video more digestible. We're going to build up kind of from the basics all the way to the complexities that you might expect to see in an interview itself. And along the way, we're going to cover a lot of really rich topics: stream processing, approximation techniques, count and sketch, time series databases. The goal here is to try to build up your toolkit for handling problems like this, because in a lot of cases, the exact requirements and the exact trajectory that you're going to follow in the interview is probably going to be a little bit different than what we're covering here. And the goal is either A, you've worked on data-oriented systems and you've got a better idea for how to solve problems like this, or you haven't worked on heavy data processing systems and you're starting to build some intuition about how these systems work. That's the ultimate goal. So keeping in mind that you're not trying to memorize an answer here. You're trying to understand the concepts so you can apply them in a variety of different scenarios. Now, quick plug on this. I published the guide for this problem. You can see it on our website. I'll include a link in the description. This is basically going to cover a lot of the same ground that the video covers. We may touch on a few topics that aren't covered in the article, but for the most part, we try to keep the article up to date with the video. I won't be able to make any edits to this video, thanks YouTube. So, if there's errors or errata, we'll try to include them in the description. Now, in the article itself, you can highlight and make notes. You can add comments and ask questions. We try to be active there in answering them, or our community is. And there's also a feature on our website for premium users, which we call Tutor. And what Tutor does is we basically have an AI that allows you to ask questions about our articles. And it has in its context all of the articles and all of the insights that we have across Hello Interview. So it's going to be much more informed, answering questions like, what's Meta's interview process like? Or what do interviewers tend to care about than, say, generic ChatGPT might? Final comment on this, we have a guided practice for this problem on our site, a way for us to work through problems with you with guidance. And we found this to be incredibly effective for people who are especially new to system design interviews, but also just trying to knock off some rust before the actual interview itself. So we start out by giving you some requirements, walking you through our delivery framework, which I'll talk about in a minute. And then what you'll see is you're basically given a whiteboard, just like a real interview, and ask questions. Like, let's walk through the non-functional requirements of the system. I can be lazy and put just a small number, click get feedback, and then shortly thereafter, I'm going to get a response from the AI that's going to tell me about how I did. That's not quite it. The difference that our guided practice has from a lot of mock interview platforms is, first of all, we actually heavily constrain the AI by looking at all of the different ways that our users have gone through different problems and then judging them using staff level engineers on the back end so that we can actually give you good feedback that's not just generic slop. The other thing that our guided practice does really well is it's much better at teaching. So it's a really immersive platform for you practicing for your system design interviews. Definitely worth checking out if you haven't. But let's go ahead and get into top K. Now, when you're in a system design interview, your interviewer is probably going to plop some question, either verbally, they're going to say, hey, design top K YouTube video, or they might paste something on the screen, but usually you are going to be in the driver's seat for the rest of the interview. And what we found through thousands of mock interviews is that candidates who have some structure oftentimes have a leg up to candidates who don't. Because if you just come in and you've got a lot of thoughts and you want to get them down, it can be very hard to get the right pieces over to your interviewer that they're going to need for the evaluation. So we created what we call our Hello Interview delivery framework. And I'm going to follow this structure in this video just as an illustration. The way the framework works is that we are going to first set up our problem. We're going to ask our interviewer lots of questions about requirements. For top K, this is really important, and we're going to spend a fair amount of time here. Next, we're going to get into core entities, which are really like the nouns of our design. They aren't as important for top K problems, but they're really important for a lot of problems. So we'll go through it anyway, just so you can see what it looks like. And then we'll come up with our API for our system. If you can think about it, having an API gives us a way to start the problem. If we can figure out how to design a system that satisfies our API, then in some sense we're done. It's the root of what we need to build. For some problems, we will talk about a data flow. We're not going to talk about it here, but it is applicable for a lot of back-end data-oriented systems. And then next, we're going to go into our high-level design. This is what everyone is normally familiar with, where we're going to be drawing blocks on the screen. With our high-level design, we're going to try to design a system that minimally satisfies our functional requirements. And the reason for that is twofold. One, we want to make sure that we have a working system by the end of the interview. And if we start to optimize prematurely, there's a good chance that we actually won't be able to get to all of the requirements. The second thing is that it's oftentimes much easier to take a working system and optimize it than to take an optimal system and make it working. You'll find this to be especially true of real production systems, and so it should be no surprise that it actually applies in the interview setting. Now, once we have a working system, then it comes to deep dives. And these are going to be the places where we are going to start to layer on our non-functional requirements, latency and scaling. This is also a place where our interviewer might ask us additional questions. They might change the game. They might throw in new requirements. And what we want to do is leave ample time to be able to go into these details after we've laid the foundation of a working high-level design. And so that's what we're going to do with this top K design. Let's start with requirements. Requirements can be broken down into two categories, our functional requirements and our non-functional requirements. Functional are really about what our clients see or what our users are expecting out of the system. It's kind of the whole reason the system exists in the first place. But in many cases, this is determining what the system needs to be able to do. The non-functional requirements are more constraints. They're going to be how it does that work. And this might be how the resources are limited, what sort of data processing is possible. There's a bunch of things that we can talk about. But it is really useful for you to separate this discussion. Now, sometimes when people hear an infra problem like top K, they're thinking to themselves, well, the requirements as stated by the interviewer are pretty complete. They told me to build a top K system. Let me go for it. That is absolutely not true. And you do need to spend time clarifying these requirements because there's a lot of ambiguity. And for this problem in particular, small changes in requirements imply dramatically different solutions downstream. We see this again and again, especially from candidates who go into an interview and then are completely flabbergasted that the interviewer doesn't like their solution, in many cases because they are applying a solution that works for one set of functional requirements to a different set of requirements. So please take your time here and showcase your ability to build up the concreteness of your requirements and the spec that you're building behind. So our interviewer told us to get the top K most viewed videos. Let's go ahead and put this down on our requirements so that we have it. A really good question for us to ask is, what time windows does this apply to? If we build a system that tries to get the top K all-time most viewed videos, it's actually not going to change a lot. I think Gangnam Style and some Justin Bieber video are probably near the top and likely aren't going to change on a day-to-day basis. It's actually kind of uninteresting. And so we may ask our interviewer or make some assumptions here, but if we ask our interviewer and say, hey, what time windows do we want this over? They might say, well, I want to be able to do all time. I'd like to be able to find Gangnam Style, but I also want to find the top K most viewed videos over the last week, month, maybe even day or hour. This addition of time windows to the problem adds a lot of interesting complexity. It also adds a lot of ambiguity to our requirements. What do these time windows actually mean? One example of this is the difference between what are called tumbling or sliding windows. So if I say last week, for a lot of people, what that means is the period between Sunday and Sunday of the prior week. So what you see with tumbling windows, and that's an example of a tumbling window, is they always start on fixed boundaries and last for the entire duration. If someone says last week, you can assume they're talking about a tumbling window of weeks. But it is possible for them to have been referring to the last 7-day period that has just passed. That would be an example of a sliding window. So right now for me, it is Saturday afternoon. And on Saturday afternoon, a sliding window of the last 7 days would go from the prior Saturday at Saturday afternoon all the way through to the current period. And that would continue to move forward. As time advances, that window moves forward. That 7-day period that we're talking about changes. So a good strategy in an interview setting is to make an assumption that things are simple, especially from the functional requirements, and then run it past your interviewer. So you might say, I'm going to use tumbling windows. So the last month is going to be the period starting on, the month start, the first day of the month, all the way until the end of the month. Is that okay? And the interviewer might go, sure, yeah, that'll work. I might also clarify that for a week, I'm going to talk about 7 days. And then for a month, I'm going to talk about 28 days. Do I really want to support calendaring? Absolutely not. So we're going to try to simplify things down here to make our lives a little bit easier. There are some other problems that might come out. Like when we say we want to view all of the videos over the last month, do we want to be able to view what happened in October of 2019? Do we want to be able to support arbitrary time windows? I'm going to go ahead and say that this is below the line. I'm not going to support arbitrary time windows. This is more of a general analytic system problem versus a more specialized system that's calculating top K. And as such, it's a little less interesting from an interviewing perspective, but it's useful for us to be able to say, no, this is actually completely out of scope. We can continue the conversation here for as long as we want. While I don't think that you should neglect the requirements, it's also possible for you to spend too much time here. And one way that I find candidates spending too much time is enumerating a lot of things below the line, which are basically things they're not going to be covering in the interview. So if you have some additional time, go ahead and tell your interviewer, these are things that I'm not going to handle. But if not, keep to your actual in-scope functional requirements and then keep moving. Next, we're going to talk about non-functional requirements. The non-functional requirements, like I mentioned, are the constraints on the system. They're about how the system does its work as opposed to what it's doing. If you look in our delivery framework under the non-functional requirements section, we actually have a bunch of different categories which you can use to start to get your brainstorming going. But keep in mind from an interview perspective, it's actually more important that you get useful non-functional requirements than that you have comprehensiveness. So don't memorize this list and then try to come up with one non-functional requirement for each category. That's going to be completely overkill. For this system, it's probably going to be useful for us to talk about latency, scale, how the calculations are actually happening. So let's go through those. We'll start with latency because everybody likes to talk about latency for these systems. With our latency, there's two latencies that we're concerned with. One is on the right side. After a view happens, how does it enter our calculations of top K? And then we have latency on our read side. Users make a request. They want the top K most viewed videos. How long does that take? On the right side, there is the reality of distributed systems is that a lot of times things will be delayed or they'll be out of order at scale. If you have retries in your system or if there is network congestion or packet loss, it means things can happen and you can learn about them oftentimes significantly later. So one non-functional requirement that's useful for this problem is to say, let's pretend that we have 1 minute between when the event happens and when it is tabulated in our top K. This is going to be useful for two things. One is if you're thinking forward, you can imagine that we're probably going to use some caching in this system. And the caching has a TTL. It's basically how long can we keep around data before it's too stale to serve to our users? If we set the cache TTL to be longer than this 1 minute, that means that we're going to violate this non-functional requirement because it means that a view could have happened, say 1 minute ago, and we have a cache TTL of 2 minutes, but we're serving a cache entry that's 2 minutes old. So we violated this non-functional requirement. So in some sense, this sets an upper bound on our cache TTLs, which is super useful. Another thing that it's useful for is solving that out of order problem. If you have a video view that happened at 9:59 and 59 seconds, but you didn't hear about it until say 10 o'clock and 6 seconds, you still want to be able to include it in our top K. We want to make sure that it shows up. But if that video view doesn't appear to us, let's say for 3 minutes, maybe it got lost and put on a truck somewhere, and then eventually somebody called our service with it, then we can safely ignore it. So what this is basically doing is giving us a pass to ignore events that are happening more than 1 minute ago, at least at the time that we process them, which is quite useful. The next thing we'll talk about here is the read latency. For systems like this, interviewers typically want you to be pretty aggressive. And you can kind of think about things in 3 buckets. The first bucket is like cache hits. Those are usually single-digit milliseconds. It can't apply in every scenario, but it's the best experience when it can happen. And so single-digit milliseconds is the gold standard for distributed systems. The in-between for most APIs is something on the order of tens of milliseconds. Most well-tuned APIs operate in this vicinity. They might not in the limit, so they might have a P99 request that take hundreds of milliseconds. But tens of milliseconds is usually a pretty good one. And then finally, you have search APIs and LLM APIs that can take hundreds of milliseconds to seconds or maybe even minutes. For this system, we're going to choose that middle ground. We're going to say tens of milliseconds to retrieve the top K. And this is just going to give us an idea about what kind of preprocessing or caching do we need in order to achieve this aggressive read latency. Next, I'm going to talk a little bit about scale. It's useful for us to think about what dimensions of scaling are important. And for this problem, there's 2 dimensions that are really important. One is the cardinality that we need to handle. Cardinality is like the number of unique items. If we're calculating the top K of 5 items, it's not going to take me very long at all. I can just sort the list. If we're calculating the top K of billions of items, I can't actually do that sorting in real time. I'm oftentimes going to need to do some sort of pre-computation. So for this, I'm going to assume that I'm handling billions of videos. I'm going to put a TBD on this and basically tell my interviewer, I'm going to come back and refine this estimate a little bit later. But I want them to know that I'm thinking about the number of videos that are going to be included because it helps me to reason about storage. The next thing I want to think about is what kind of write volume do I need the system to support? And maybe for this, I'm going to assume hundreds of thousands of views per second. I'm going to also put a TBD on this because I don't know if hundreds of thousands of views per second is reasonable for YouTube. I might ask the interviewer, do you have a specific number in mind, or should I try to estimate this? But I know that this number needs to be big, and I know that this is going to be one of the harder things for me to handle in this particular system, so I'm going to go ahead and include it here. The last non-functional requirement that I want to address before we move on is whether I can use approximation. I'm going to say for this problem, I need precise results or no approximation. And the justification for this is the same one that I used in assuming tumbling windows for this problem. Getting precise results is oftentimes much easier than designing a well set up approximate system. Now, I'm going to walk into one of our deep dives to talk about approximation and how you might use it to make an even more scalable system. But generally speaking, for interviews, most of the time, interviewers aren't expecting you to know about things like count, min, sketch, especially at more junior levels. And so being able to say explicitly in your requirements, this is what I need to handle, helps to clarify that you're not even going to consider some of those solutions. I've got 5 non-functional requirements here. I've spent a fair amount of time. I'm going to go ahead and stop here. I might ask my interviewer, are there any other things that I really need to cover in my requirements, or can I get started? And they're going to give me the green light to go ahead. Now that we've got the requirements stated, our goal is to get to an API. And the API is basically the foundation on which we're going to build our high-level design. If we've got a set of APIs that we need to implement, then we can make sure our system actually implements those APIs. And if they have, then they've satisfied our requirements. So we're slowly building up toward this solution. For this problem, the next step is we're going to establish what our core entities are. Core entities are basically nouns that we're going to use to talk about the problem. For top K, this actually isn't super interesting. We've got a video, which is basically what people are watching. We've got a video view, or just a view that we can talk about. That is when an individual watched a video. And then finally, we have a time window or a duration that we're able to use to query the API. The reason that we're enumerating these nouns is because it's useful to use in designing our API. But this might seem overly simple because in other problems like Ticketmaster, there are more entities that you might need to think through. It's still a useful exercise, even for an infra problem like this, to create these entities. But we don't recommend you spend a bunch of extra time here. Oftentimes, the entities and APIs are a little bit more straightforward for some of these backend systems than they are for full products that you might need to design. For my API, I need a way for my users to be able to get the top K videos by view for a given time period. I'm going to use a REST API for this. It makes it easy on my clients. It's very standard. All interviewers are going to know about it. And I'm going to query for /views/topk. I'm going to pass in a window. I'm going to pass in a K. And then I'm going to have this return basically a video ID, which is maybe a string, and then a views count, which is probably an integer. And it's going to be an array of those. My clients will just assume that this list is already sorted. And in some sense, if I go back to my functional requirements earlier, I've got my top K most viewed videos. I've got my top K most viewed videos for last month, week, and hour. That's going to go in my window. And I've got my tumbling windows. This is the only API that I really need to create. So from this, I am done. You might be asking yourself, do I need to include pagination here? But remember that in our requirements, we've already limited K to 1,000. So at worst case, this is going to be a couple kilobytes. It's not a big payload. You could add it if you wanted to. You're not going to likely create infrastructure around that pagination just because it's such a small number, but don't stress out if you don't need it. The important thing here is, and especially for more senior candidates, I don't want to blow a bunch of time on uninteresting parts of the interview. My requirements were interesting. I wanted to spend some time there. I'm going to spend a lot of time in my high-level design and deep dives. But it necessarily means that I can maybe skip a little bit of the time that I would otherwise spend in my entities or API for this particular problem. All right, now that we've got my requirements set, I've got my core entities, I created an API. This is functionally the contract that I need to implement. We can move into our high-level design. The high-level design, remember, is about how we can make the system functional, how we can satisfy those functional requirements. And we're going to do this as simply as we can. We're going to kind of take some shortcuts here and do some things that are not scalable. And the reason for that is we want a base that we can then optimize and solve those problems in our deep dives. So that's what we're going to do. For this particular problem, I am going to take a shortcut, and it's one that I would recommend that you do. And I'm going to assume that there is a video views topic sitting in Kafka somewhere, put together by some other service on YouTube. Note for this problem, I'm not being asked to design YouTube with a top K feature. I'm only being asked to design the top K feature. And as such, instead of making an API where I would accept a view, I am just going to assume that someone somewhere is keeping track of those views in a Kafka topic. This is a really good assumption. In a lot of systems like this, you're going to have topics that are recording some of the most important events in your system, and then systems can consume or subscribe to those topics and then do the things that they need to do. I'll link in the description to our event-driven architecture blog post. You don't oftentimes see this show up in system design interviews, but it is a very popular way to design systems, and having big granular topics with important events can kind of be taken for granted for a lot of systems. Now, I want something that is going to consume these views. So I'm going to create a service I'll call view consumer that's going to read off that video view Kafka topic. I can, of course, scale this out if I need to. I'm going to assume these video views are probably partitioned in some way so that it's scalable. Remember, we have a ton. We have hundreds of thousands to millions of views that are coming in every second. So this is going to become a bottleneck very quickly. But let's pretend I have a service that's reading from these. And then I need to write it to a database somewhere. So let's go ahead and add a views database. I'm going to use Postgres for now because it's a convenient way for me to get started. And we'll try to decide where we might hit some scaling limitations that might make this intractable, but it should definitely work for now. It'll be useful for me to have some sort of table structure where I'm going to store the data here. I'm going to put my video ID and I'm going to put the number of views in there. And with this, I've got a really simple system that's going to be keeping track of all of the video views as they come in. Whenever a view happens, my view consumer is just going to update the record for that particular video ID. It's either going to create a new record with the view count being 1, or it's going to trigger an update statement for a particular video ID, and it's going to add 1 to the views. And now I have in this video views table the count of all views for all videos. This is really useful. Now we can start to talk about what the read side of the equation looks like. So let's go ahead and start with an API gateway just to make things nice and standard. I'm going to create a top K service, and that service is going to make queries to my views database. Since this is a SQL database, I can actually trigger SQL queries. So let's talk about what that SQL might look like. I'm going to do a little copy pasta here so we don't have to see me type SQL. But what I'm going to do is I'm going to select the video ID and the corresponding views from my video views table, and I'm going to order by the views column. Finally, I'm going to limit to my top K items. This SQL query will actually get me the all-time top K viewed video out of my database, assuming my data is structured like this. Now, as a micro optimization, and I don't encourage you in the high-level design to do lots of optimization at this point, but it is useful for you to be pointing out things to your interviewer that might be suboptimal, either to address immediately or as part of your deep dives. This query is only going to be fast if I have an index on views. And the reason for that is otherwise, if I don't have this index, what my database needs to do is read every single row in the table, and it needs to sort them all, and then it will give me the top K. I think Postgres might actually implement this with a heap. I'm not sure. But regardless, it's going to be dramatically faster if I have this index. The index on views is basically like a sorted list. And so when we run this query, the query planner is going to go look at that index, and it's just going to go grab the first K items off that list. It's actually very fast. So now we've got a system that both writes our views as they come in, and it reads them. Now, some of you guys in the comments are going to be puking right now. You're going to say, this isn't scalable. This couldn't possibly work. I agree with you. And I'm going to make notes of this to my interviewer. I know that this system doesn't scale. I'm going to start with a basic system, and then I'm going to optimize it as we go. If you are a staff level engineer, you probably don't need to start with a system as basic as this. You can skip some steps, and you can trust that your experience is going to be useful. But if you are a more junior engineer, then starting with a more basic solution is going to yield dramatically better results than if you try to jump straight to an optimal solution. So I would highly recommend it. But with this, I've solved my first requirement, and we can move on to that next requirement. My next requirement is to be able to support those window queries. That's where my user specifies they want to see the last month. And with this system as it stands, I can't answer those because remember, my video views are summed over all time. I can't distinguish the views that happened last month from those that happened last year. They're all bungled together. And so I need to make some changes here. The simplest change that I can make to this system is to add a timestamp to this table. I still probably don't want to record a row for every view, although I could do that if I wanted to make the most basic high-level design possible. Instead, what I'm going to do here is I'm going to round the time down to the nearest hour. And this timestamp is going to represent the beginning of the hour that view happened. So I'm going to have a bunch of buckets for every video for each of the hours that they're there. I'm not going to be able to use the SQL that I had used previously. I'll paste some more SQL in here. This is probably going to be the query that I'll use. And if you're not familiar with SQL, that's totally okay. It is important that you understand for problems like this, how data is flowing and what's happening. So you need to be able to reason about this conceptually. If you haven't learned SQL before, I highly recommend you learn it. It's actually going to be very useful for you as an engineer. But let me walk you through what this means. Basically, what I'm going to do is I'm going to grab all of the records in this table that fit within my window. So I'm going to choose the hours that fit between the beginning of last month and the end of last month. That way, I'm only looking at views that have happened over my window. The next thing is I'm going to group these all together by the video ID and then sum up those views. I'm basically going to aggregate them so I get a table of video ID to the total number of views. And then finally, I'm going to sort that table and then return the top K elements out of it. SQL makes this seem really easy. And in some sense, changing this SQL is not too hard. But where my previous SQL could return very quickly by virtue of that index that I had, I deliberately deleted the index here because it's not really going to help me all that much. I think if I wanted to, I could add an index on timestamp. And then what that would do is just make it so that way my query planner can ignore rows that are outside the window that I have. But for this query, I need to read every single record in the table that sits within that window. And I have to do all the aggregation. So this is going to be dog slow. If the other solution was suboptimal, this is like suboptimal. And I'm probably going to note that to my interviewer and say, I realize there's problems here. I'm going to get to these in the deep dive. But generally speaking, this system satisfies my requirement. I can query for any of the windows that I have last month, last week, last day, and I can get the top K value, even if it's outside my non-functional requirements of returning in milliseconds. So this gives me the base to get into some of those deep dives that we talked about, and that's what we'll do next. In terms of optimizations and deep dives, let's start with the lowest hanging fruit first, and then we'll progressively get to the more complex topics. This gives us the most bang for the buck from an interviewing perspective. We can impress our interviewer with how quickly we were able to move through things and save the slow stuff that requires a lot of brain power for a little bit later. So the first thing that might stick out to you all is on the read side. Right now, the query takes a long time, and our promise to our users is that we would return in milliseconds, tens of milliseconds. And so we are not satisfying that non-functional requirement. How can we make it happen? Your brain should start to light up here with two options, caching and pre-computation. Let's talk about what both of them would look like. So for caching, what this might be is we set up a Redis cache over here. We can use a read-through cache. So we can go and query the Redis cache and see if we have an entry for the top K query that we have. The keys of the Redis cache might be the time window, maybe some truncated or rounded timestamp. And then the values are basically the responses that we're going to give to users. If it's there, then we can return our results to our users in single-digit milliseconds. The gold standard, that would be amazing. If we can't hit the cache, if we have a cache miss, then we need to go to the database and get the actual value. Remember, this is going to take forever right now, so this is a very bad situation. But when we get those results, we can simultaneously return them to the user so that they get them as fast as possible and write them in the cache so that subsequent requests are going to be much faster. As a solution, this is pretty elegant, right? We just added a cache, and now say 99% of our requests are going to be served in single-digit milliseconds. Amazing. And only a few of our requests are going to end up hitting that database and then taking minutes to hours of time. Maybe on average, we're actually in the double-digit milliseconds, but this is a pretty poor design overall. With distributed systems, what you want is consistency. The more predictable things are, the more effectively you can build on top of them. And this service is Russian roulette. I might get a cache hit. I get the best service I've ever worked with. It's blazing fast. Or I might get the worst service that I've ever touched. I'm timing out. It's taking hours. What the heck is going on? So this is not a particularly good situation because of the cache misses. But the nice thing about the cache misses is they're somewhat predictable. We know that we are going to have a new last hour every hour. And so we can anticipate when we're going to have the cache need to be refreshed. And so a better solution is probably one where we actually do some pre-computation. So let's add a TopK cron service. And this is going to every hour run that query and populate the cache. Now, when our TopK service queries the cache, we can hope that it's always there, that we never have a cache miss, even as the hour expires. This is preferable because you don't have a Russian roulette scenario, but it does have some downsides. What happens if this cron fails? What do we do then? Well, a terrible solution, and one that might come to mind, is to have the TopK service hit the database then. So if we can't find it in the cache, we'll go get it ourselves. And the problem with this is this TopK cron is very infrequent. It's low load. We're basically making one request an hour, or maybe a few requests an hour to the database. But when we have a failure here, suddenly our TopK service is making thousands, maybe even millions of requests to the database simultaneously because they're all going, why do I not have my cache entry? I'll go get it myself. So we've amplified the load on the database dramatically. If this cron was failing because the database was under load to begin with, we've made it so much worse. So we almost never want to do something like this. What we might do instead is to basically keep our entries in our cache for a bit longer. So maybe we will store the window and then some truncated timestamp as the key in our Redis cache. And we'll set the TTL to something long, like, I don't know, 30 days. Now, when our TopK service queries the cache, it's going to try to get the most up-to-date information for the last hour. But if it can't find it, it's just going to fall back to the last window. Now, this violates our SLAs, right? It means that we are not satisfying that 1 minute time between when an event occurred and when it was tabulated. But it's a better failure mode than the alternative of tearing down our system and making it really hard to bring back up. So it's a better option from that perspective. So overall, you can probably improve the read performance dramatically by simply pre-computing with a cron that runs on predictable intervals and stores information in a cache. That's the easiest way to scale and meet our read requirements. With the read side partially solved, let's turn our attention to the write side of the equation, which is just a disaster in the current design. I want to take a step back to really put some numbers to this problem so that we can think about this more quantitatively. And I'll caveat this a little bit. For Hello Interview in general, what we find is that a lot of candidates jump into problems with a lot of back-of-the-envelope estimations that don't actually help them in their design. And interviewers aren't looking to see whether you can do mental arithmetic as a condition of your employment. If they are, they suck. You shouldn't work for those companies. So generally speaking, what they do want to see is how well justified are the decisions that you're making. In this case, I know that these writes are bad. I know that there's billions of records in here and that I've got way too much load on this database, but I don't really know how bad it is. So let's try to figure out how I might be able to arrive at this. First, I might ask my interviewer to give me some numbers, like how many views are we expecting? And maybe they tell me there's 70 billion views per day on the platform. Generally speaking, when people are designing systems, they're not usually thinking about daily or yearly or hourly quantities. They're mostly thinking about what's the number of writes or reads or transactions per second. The easy way to convert a views per day to views per second is to divide by 100,000. The actual number is 84 something. You don't need that actual number. You are doing mental arithmetic here. So 70 billion over 100,000, well, that is 700,000 views per second. This is a really useful quantity for me because it tells me exactly how many writes I'm making to my database currently. Remember, every view is a write, so I am triggering 700,000 writes per second. Postgres, generally speaking, might be able to handle 10,000 writes per second. Probably not going to be able to handle 700,000 writes per second, especially if we have more complicated indexing. There are some certain conditions on which you could support higher load on Postgres, but this is just telling me, hey, I've got a lot of writes here that I probably can't handle. Another quantity that I might want to know about is about the size of this table. I want to know whether this data is becoming insurmountably large. And the way that I'm going to do that is I'm going to start with the number of videos. Maybe I'll make an assumption here, or maybe my interviewer will tell me, let's assume they tell me that there are 8 views, videos on the platform. This is a lot. I would assume most of those videos are never being viewed. I'm going to multiply this by a simple quantity. I'm going to say there's 8 bytes per video ID, and then 8 bytes for the views. That's 16 bytes. This is 4 times 16. Billion, I don't have a quantity here. This is a billion. Billion is also a gigabyte. So it's 64 gigabytes for storing a table of all video IDs and their respective counts. That number is pretty large. A lot of engineers probably aren't working with data sets that big on a regular basis. But when it comes to data processing systems, gigabytes are not that impressive. In general, there are multi-terabyte NVMe storage that, even a run-of-the-mill database would be able to support. So we don't have to be afraid of this number in isolation. We do have to be afraid of this number when it multiplies out. And remember, with my design, I am storing video views on an hourly grain. So I have one of these tables every hour. So 64 times 24, that's the number of daily gigabytes that would take. Now, do keep in mind that this is a little bit more efficient because it is what's known as sparse. My video views are only being recorded when a view actually happens. And the vast majority of videos in this catalog are getting 0 views. They don't have any rows in this table. So this is a strong upper bound on the size of each of these basically partitions in my data. But it does tell me that, hey, this is somewhat manageable as long as I can make sure that I'm not keeping too many copies of this. So now I've got 2 quantities here. The 64 gigabytes tells me a bit about the storage, and then the 700K tells me a bit about the throughput. So let's come back here to talk about our writes. Well, our video views Kafka topic could easily handle this 700,000 views per second. Kafka is very scalable. These messages are only a video ID and maybe a timestamp, so they are tiny, and this can scale out indefinitely. The way that this would be scaled out is the video views topic would be partitioned by video ID. So basically, if I was a consumer of the video views topic, I would probably want to choose a limited number of partitions rather than swallowing the entire global fire hose and filtering down to the videos I care about. I can actually only read those video views that are going to be important to me. That gives me a chance to scale out my view consumer. And when we think about write volume, this should be our first instinct. We should try to figure out how we can partition or shard the inputs that are coming into us. So our video views topic is already going to be partitioned by video ID. Our view consumers can be partitioned by video ID. So we'll have each view consumer will handle a subset of those video IDs. And then finally, we can shard our Postgres database. We can have it such that each instance only contains the video views for a subset of those video IDs. I earlier gave you a number. I said Postgres, generally speaking, can handle, say, 10,000 writes per second. This is a rough ballpark, but if we make that assumption, we would need 70 shards of Postgres and probably 70 view consumers in order to consume this full write volume. Now, that isn't without its downsides. First of all, it's a ton of resources, but it also means that when we query, we need to query separately each of the shards. Now, fortunately, this is pretty basic operation if we just want the top K most viewed videos. What we can do is make the same query to every shard. So if we want the top 1,000 most viewed, we're going to say for each shard, shard 1, shard 2, what is your top 1,000? And then we're going to merge them all together to get the global top 1,000. You can mathematically guarantee that the global top 1,000 must be within all the union of all of the local top 1,000s. So our query trivially scales. Now, of course, it's not nice that our cron job has to query 70 databases, but arguably that's going to be 70 times faster than what it's currently doing with a singular instance. And we already have a lot of affordances that we've developed here to allow this cron to take additional time. Because one of the things that you'll be worried about when you're querying lots of shards like that is some of those requests will probably fail, and they'll need to be retried or sent to a replica or something along those lines. So our first line of defense for scaling out the right volume in this problem in kind of the most naive way is by partitioning and sharding. After sharding and partitioning, we have to get a little bit more creative in order to improve the performance of our system. In this case, what we'll do is we'll work through our scaling rights pattern, which is basically a list of different strategies that we can employ in order to improve our write efficiency. You can find this on our website as part of the premium offering, or I'll cover it here. So the next step for us in scaling writes is for us to consider batching or aggregation. Currently, every video view means a write to our views database, but our video views table is at the hourly grain. So we don't really care about every write as it happens. We only really care about the sum total of video views over a tumbling window hour. So can we reduce the writes to our database by aggregating or pre-aggregating or batching in our view consumer? Sure, we can. So what might that look like if we don't use any technologies? Well, what we could do in our view consumer is we could keep a map in memory of all of the views that we've received and haven't flushed out to the database. Then every hour, what we can do is write those into the database. And in that sense, our problem is going to largely go away. The number of writes that we're going to make is now bounded not by the number of views, where 700,000 times a second, but bounded by the number of videos that had views in a particular hour. You would expect that that number is a lot smaller. It is a problem that we are waiting to do all of our writes all at once at the end of the hour. So that means our database is sitting around, it's chilling, and then suddenly it's slammed. But it's slammed with substantially lower volume than this constant streaming updates that we are otherwise sending it. Now, if we do this ourselves, the problems mount from here. The first problem that we have is failures. So if this view consumer fails while it has an aggregate in memory, you might wonder, do we lose those views? It's obvious that the Kafka topic will always be the source of truth. So as long as this Kafka topic has retention, then we can always have our view consumer rewind in the Kafka topic and then read from there to catch all the views that it missed. So even if we had a view consumer fail, say 45 minutes into the hour, what it could do is then start reading views from the beginning of the hour and then hopefully eventually catch up. That would be a good recovery strategy. The problem with that is that it requires a lot of scale. If we set our view consumers and we scale them such that they're able to process 700,000 views per second, they don't have any headroom to catch up. Pretend I am that view consumer that's 45 minutes behind. I'm still processing 700,000 views per second because that's my capacity. And I'm always going to be 45 minutes behind. I'm never going to catch up. If we double the amount of capacity that we have, so we have 1.4 million views per second of view consumer capacity, then that means that we are able to work through 1 second of backlog every 2 seconds, because half of our capacity will be taken up by just staying up with the views as they come in. And then the other half, the remaining 700,000, allows us to start to catch up. And so that means if we are 45 minutes behind, it's going to take us 45 minutes to catch up. And that means that we are definitely going to be late for the next hour calculation. We're going to be 30 minutes late. So the problem with using a Kafka topic with retention in order to catch up after a failure, if we're keeping really big windows like this, is that it takes either too much capacity. We need to multiply the view consumer fleet so it has a lot of wasted resources, or it's too slow to catch up. The solution that we would implement is to have some sort of checkpointing. Maybe every 5 minutes, we write the sum of views that we have in that window to S3. And then if our view consumer fails, it can read the latest checkpoint. So it can catch up to that 5 minutes, and then it can use the Kafka view stream to catch up from there. So we're no more than 5 minutes behind. That strategy of checkpointing is so common in streaming systems that they built an entire framework around this, and it is called Flink. So in this problem, we could go and do a bunch of aggregation in our view consumers, or we could do the windows in Flink. We'll say Flink hourly windows. And what that looks like is we have a Flink job that runs in a cluster. And then Flink is going to handle our checkpointing internally. And then Flink is going to have special sources like for Postgres or S3 or for Redis. And so what's going to happen here is that Flink will manage internally that checkpointing. And then we'll write our video views on the hourly grain as they occur. Now, Flink is a funny technology to trot out in interviews, in part because Flink is very powerful. A lot of system designs can be expressed entirely in Flink jobs, which is nice. You can write a Flink job, which is just a lot of Java code, deploy it to a cluster, and then get rid of some or much of what you see in this picture. The problem with doing that in an interview setting is that sometimes interviewers are not familiar with Flink. So you might be expressing a solution that they don't understand, or they might feel like you're oversimplifying the problem or maybe hiding all of the complexity behind a technology. And then what they're going to want you to do is to explain how all the pieces work. Can you explain to me Flink's checkpointing algorithm? Or can you explain to me how tumbling windows work internally to Flink? So I'll say, in general, I would use Flink sparingly in your interviews, but many people are familiar with this application of using Flink as an aggregation platform, basically, for streaming data. And so this is generally a safe application for this problem. And then what we've done here is we've substantially reduced the number of shards that we're going to need in our views database, in part because Flink is taking the bulk of the load in processing these views and then producing just the hourly grained updates before we write it to our database. Okay, so we're slowly chipping away at this problem, and we've got our read latency down much better. Our write throughput to the database has decreased. We still have a problem here in that the cron is making these very expensive database queries. And I want to elaborate a bit on how expensive they are, and then talk about how we can start to optimize this. So if we think about our database queries, what they're doing is they are grabbing all of the video views across all of the hours that are included in the window. The pathological case that we need to solve here is that we have an entire month that we're trying to aggregate. So we've got 24 times 30, 300 hours that we need to pull. And what we're going to have to do is grab every row by hour, is grab every row by hour, which is probably going to be on the order of hundreds of gigabytes of data. We have some efficiency because this is sparse. Remember, not all videos have views every hour. So this isn't a full 64 gigabytes times that 300 number, but we still have hundreds of gigabytes of data. And then in our database, the next step is they are going to aggregate by video. So for each video, we're going to get all of the hours and we're going to sum those up. So now we've got total. This is probably going to be tens of gigabytes. Most of our videos are going to have views over the month. We should expect that this is less sparse. And this is not sorted in any way. These are just aggregates. And then finally, we have to go and sort this. And the sorted value, especially if we take it down to just the top K, is just kilobytes of data. Like our output is not that big, but we are processing an enormous amount of data in order to get there. And like I said, whenever we are processing an enormous amount of data, this should be a cause for pause. Now, a lot of people will think, I've got an enormous amount of data. That sounds like a place where I should use Spark or Hadoop. And I think the instinct there is probably a good one. What Spark or Hadoop allows you to do is to scale out this computation. This is parallelizable. If I wanted to, I could have an individual machine for every video that adds across all of the hours. And then in the sorting, what I can do is have each machine sort a subset of the data. And then they can pull that data together and then merge sorted lists. That's known as a reduce operation in Hadoop. And while that does allow us to scale this out, it doesn't make this any more efficient. We're still throwing an enormous amount of resources and hardware at a problem that we can probably think more deeply about in order to solve. So what can we do here? Well, one thing to note is that our hourly windows are landing in the database, but we end up wanting to aggregate these. And so one thing we might ask ourselves is there a way for us to have hour, day, month video views? Now, whenever Flink is doing the processing at the hourly grain, it's going to update not just one record, the hour record, with the timestamp and the total views. It's also going to increase all of the views for the day and the month that that hour is a part of. So we will 3x the number of writes that we will do into our database. But now when we want to do our reads, we can actually read directly out of these tables. So we're saving a bunch of resources. I think this is a much more elegant solution than doing all of this aggregation on the flip side. And one thing that it allows us to do is it allows us to index on timestamp and on views. Remember when we had our all-time queries? Because we had the index on views and there was no timestamp, we basically had a sorted list of video ID by views, and our query planner could just grab the top K elements off that list. It was really fast and efficient. With this setup, we get the same thing. Because at a given timestamp, we are going to be sorted by views. So all we need to do, and this is basically a B-tree operation, we're going to grab out of the sorted list by timestamp and by views, the top viewed items for that timestamp for that granularity. So now our top cron is running effectively in, a constant time or near constant time operation rather than needing to do a bunch of aggregation and sorting. Now, some people might be saying to themselves, okay, well, Flink is already doing these aggregations. Why don't we just have Flink do it? Can't Flink just make hourly, daily, monthly windows? Then instead of needing to do some sort of aggregation over here, we can just land those as they're ready. In fact, if you've got those hourly, daily, monthly windows, you can also have a Flink operator that goes and sorts them and then returns the top K. And that is a potential option. You could have Flink output directly to this Redis cache. in some sense obviating both the cron and Postgres. The reason that I don't think that this is a great option for interviews in general is that interviewers don't want to turn this into one big giant Flink box. If they do, they probably want you to go into detail about each of the operators in each of the jobs. And I don't know about your preparation, but if you want to make it very Flink-centric, maybe getting up to speed there is a gamble you want to take. But it's probably not the right trade-off for most people in their preparation. But it's something that you could potentially do here. I'm just going to make a quick note and an edit here that you'll likely want to include a table that has the video views all time and keep that. Much like your hourly, daily, and monthly, you'll be adding to this as well. It won't have any timestamps, but this also can include an index on views and be queryable whenever we want to answer questions related to that first functional requirement. So if there was any confusion, yes, we'll keep that table. With that, we've reached the end of what I would consider the core of this particular solution. We've got an optimized read path that returns in double-digit milliseconds. We have a write path that is properly sharded and partitioned, that pre-aggregates data and indexes it in a sensible way so that queries can be answered quickly and users get the results they're expecting. For a junior through senior candidate, I think if you hit many of the points here, you're in a pretty good spot as it pertains to the interview that I've just described. For staff level candidates, there's a lot more that we could potentially discuss here. We can change the rules a bit. Well, what if we need to support more windows or topics? What if we need to support sliding windows? Those are all fair game for staff level interviews. Another thing that staff level candidates will oftentimes go into is how do some of these things work in particularly ugly scenarios? The views database is sharded. What if I have all of the views for a particular timestamp for one shard, but not another shard? How do I detect that downstream? And how do I make sure that my clients understand the results? Some of these things can get a little bit dicey, but they're also very detailed. And so it's actually difficult to formulate the problem until you're actually in the weeds. But staff level candidates will oftentimes notice problems like that. Problems like, how do we handle out of order events? Or how do we think about timestamping the events as they enter our aggregation? These are all pretty rich topics. Now, each interview is going to be different. And as I mentioned, interviewers might change the requirements on you, or they might just give you a different set of requirements to start with. I wanted to spend some additional time in this video talking about a few variants, just to give you an idea and a starting point for how you might address these pieces. I want you to keep in mind that your job as a candidate is not to memorize every possible answer to a top K problem. It's to internalize some of the lessons that we've walked through around aggregation and batching and caching, so that when you have a new requirement, you can address it on the fly. Interviewers are not expecting you to invent novel algorithms. They are expecting you to have a very solid grasp on the basics so that you can adapt, and they want to see your thinking through the process. Everybody's going to come up with a different solution, and that's okay. There's not one right answer to this problem. It's way more important that you show how you work through it. Now, one of the earlier things that we did in requirements for this problem is that we forced our way into a tumbling window. Tumbling windows are much simpler for us to deal with. Remember that tumbling windows mean that we are centering our last hour at the beginning of the hour. With a sliding window, we're going to keep moving that window forward as time progresses. And usually there's a notion of how often that window is moving. You could do this continuously. That would be a little bit crazy. Or you could do this once every minute. And what that means is that functionally you have more windows to deal with. If you move it every minute, then with a tumbling window, you have one window every hour. With a sliding window, you have 60 windows every hour. And this gets only more perverse if you think about sliding windows over monthly periods, so on and so forth. So how can we start to think about sliding windows in a way that is tractable and doesn't require us to boil the ocean in terms of storage and memory? Well, one way to look at this is to think about how we can actually come up with a value of the total number of views in a sliding window. If we wanted at time 60 to find out the total number of views in the last hour, we would go over every minute in that hour, and then we would sum the total number of views. I'm not even going to do the math here, but add all these numbers together, and that is the quantity for the last hour at time 60. At time 61, we will have 1 new minute of views. So maybe we added 6 new views in that minute. Additionally, some of those views happened now more than 60 minutes ago. At minute 61, the very first minute, are no longer in our window. So if we think about how a sliding window works, what's happening is we can take the last window, we can add the most recent minute, and subtract the minute that happened 61 minutes ago. What that will give us is a change. So we have a +6, -5, and that means that we've added 1. This isn't actually all that complicated, and knowing this intuition, we can start to think about how our design might need to be adjusted to facilitate sliding windows. So let's try to walk through that. Currently, we are aggregating at an hourly level. If we want to do sliding windows that move every minute, we're probably going to need minute grain data. So let's go ahead and get that. Now we need to store this data because we need to have these minutes available. So let's go ahead and move our video views table, and we will have a video views minute table that has a video ID, views, and a timestamp. Instead of having our video views for an arbitrary hour, day, or month, how about we make this the last hour, day, or month and get rid of the timestamp entirely? This is just going to be the current value of the sliding window. Same thing with video views all time, but we're only adding to this. Now we can change our index to only be on views. So what would we do here? Well, when the video views come in, we're going to have Flink aggregate them per video into a video ID and a view count for that minute. At the end of the minute, Flink is going to flush this to our views database. So we're going to immediately write it to this video views minute table, all of the values. Now we need to update our sliding windows. What are we going to do there? Well, what we're going to do is, if we want to update the hour, we're going to grab the minute that happened 61 minutes ago. We're going to get all those views, and we're going to subtract that value. The minute that we just added, we're going to add. So we'll take whatever we're going to add minus the videos that need to be decremented, and then we will add the difference to our sliding window. That will update this table, including the index. And now when our top cron needs to make this call, it's going to be able to query those tables. Now our top cron can no longer run once an hour. Our top cron actually has to run more frequently. It has to run every minute. And our cache needs to not only have the truncated timestamp per hour, it needs to have basically the minute of that timestamp. So this is going to run more frequently, but this is super efficient. Remember, since we have these tables already sorted by views, all we have to do is grab the top item, and we already have an index, or top K items off this, and we already have the index here. So, functionally, the data is already ready. Now, what this does is it increases the amount of writes that we're going to need to do, and we're making reads from the database, which is a little bit unusual. We're basically using this as state for our system. But that would be one solution that you could use to implement sliding windows in a system like this while retaining all of the performance characteristics that we talked about. Now, like all of our other solutions, there are ways that you could do this in Flink as well. We could use Flink sliding windows. Flink has both tumbling windows and sliding windows. And the way that this works is that Flink will create a new window every interval. This is called the window slide. We've been talking about a window slide of 1 minute. So we will create a new month-long window every minute. And that window will be a month long. It will continue to accumulate over that time. If you're grimacing right now, you're thinking about this correctly, because what this is doing is it's multiplying the number of windows that we need to maintain by the number of minutes in a month. So we could externalize this storage to something like S3 or ROX. There's a lot of ways that we could try to optimize this Flink job, but these sliding windows, especially with the slide that we're talking about, are not going to be very efficient. Now, that's not to say that you can't build the solution that I just described natively in Flink. You could keep as state these minute level views externally, and then have those recorded and checkpointed alongside the Flink jobs. It's entirely possible for you to wrap this up in a Flink job. I am saying that Flink's native sliding windows will be quite inefficient at this task. I'm going to make one more note on the sliding window solution that, generally speaking, sliding windows that are a month long probably don't make sense from a product perspective. It's always a bit dicey as a candidate to try to push back on requirements from an interviewer. So if they tell you you need a sliding window at a month, you probably need to figure out how to make it happen. But if they haven't explicitly stated that, it might be a good idea for you to show some judgment and say, we probably don't need sliding windows at this granularity. Sliding windows at an hour might make sense, but at a month, maybe a tumbling window is fine. Those videos aren't going to change very much anyway. And so people aren't expecting that they're going to shift every minute. For you, I think being able to show the trade-offs and what would be required, being able to say, here is the additional infrastructure or here is the additional memory that's required to make this feature. And then being able to say, well, we can dial this back for our higher windows and then we can keep it granular at lower windows is oftentimes a nice set of trade-offs that really shows engineering maturity. And then oftentimes something that I hear from candidates at higher levels. The last variant that I want to cover is if we relax that requirement to have a precise result, if we wanted to have an approximate solution to the problem. Well, why might we want to do this? Well, Top K, we have to think about the applications. For YouTube, this is probably supporting some of their trending applications. Maybe it's a signal into their recommendation system as a candidate generator. But in a lot of cases, it's going to be secondary to the core video playing and advertising experience. Google is going to want to make this inexpensive to run. They don't want to throw a tremendous amount of hardware getting the exact right top K results if they can do it much more affordably with an approximation. A good rule of thumb to ask yourself as an engineer and then also for design interviews is, who's going to notice if the answers are wrong? And then, do they care? And I think the answer for YouTube Top K is probably not. In this case, I think approximations are a good option. Now, for an interview setting, I don't know that jumping into an approximation solution is a good idea from a strategic perspective because they tend to be more complicated. But it is a potentially good idea that, if you've got extra time and you want to showcase to your interviewer, this would be one way to do it. Now, to kind of walk you through this, I want to talk about where we would use approximation in this solution. You'll note that the really expensive part of this problem comes in our views database, where we're retaining these relatively large tables of video views and their timestamps. And the challenge here is that this could potentially get somewhat large. We aren't going to retain these indefinitely, so we would probably start to expire rows as their timestamps became old. And remember that we are basically upper bounded by 64 gigs. So when you start to talk about counts and approximation, I want you to hear count min sketch in the back of your head. Count min sketch is an approximation algorithm. You can think of it kind of like a Bloom filter, but for counts. And it's a way to really efficiently do two things. One is count min sketch will remember things that it's seen. So you will pass it identifiers. It can be numbers or strings. And then you can query the count min sketch given an identifier and get an estimate for how many times it's seen it before with some known error bounds on it. The core idea of Countman Sketch is it functions a lot like this hash table that allows us to retrieve the number of views for a video ID, but with substantially less space, and then obviously some error that we're going to throw on top. So let me show you what this looks like using a little simulator that was put together by someone in our comments. I'm actually pretty impressed by this. I will note that this is a little confusing because we are using lots of different types of hashes here, which is not really how Countman Sketch works. Usually each of these hashes would actually just be a salt. You might even use the same hash and then just use different bits of it. But the core idea is that each of these hash functions is going to take as input whatever we want to pass in, the identifier, and then it's going to give us an index based on the width of our sketch. So in this case, I have 8 columns in my sketch. I am going to, if I want to add something to my sketch and have it remember it, so foo, what's going to happen is we are going to take each of these hash functions, apply them to that input, and then the output will be the index that we should increment. So look what happened here. I added foo. For this first row, this hash function outputted, I guess this would be 0 or 7, depending upon how you want to look at it. And then we incremented the counter at that index. Same thing for each of these subsequent hashes. So what I basically got is my sketch was changed by the input of foo. If I added foo again, the hash of foo hasn't changed. And so what you'll see is that each of the indexes is the same. Each of those numbers is going to be incremented to the same value. And so I'm going to basically see all those ones become 2s. Now, if I wanted to add bar to my sketch, it's going to increment different indexes. In some of those cases, those might be overlapping, like foo and bar both have the same hash under this city hash. So that's now 3. But basically, we now have this set of counters, and we have incremented at the index of the hash of the ID for both foo and bar into that. So that's how we add items to a sketch. Now, when we want to query the sketch, we can ask it, how many times have you seen this thing before? So maybe I'm going to put hello here. And then what it's going to do is it's going to hash hello, and it's going to look at the indexes of the hash function, and it's going to grab the value there. And then it's going to grab the value from each of these rows, whatever it happens to be, and it will take the minimum of those. So you can see in dark blue, I'll hit it a few times. Those are the cells that it's querying, and the minimum of those cells is 0. Which means that I've never incremented hello into this sketch. If I wanted to query foo, I would get 2, because the minimum of all of those cells at the indexes that those hash functions coincide to is 2. The problem that we have is these collisions. Right here, we have some cells that are 3. And so the worst case scenario would be that we grab those cells and we assume that foo is actually 3. But how would that happen? It would require that we have collisions on all of the cells that foo has occupied. And the probability of the collision is based on the number of hashes. This is the height of the sketch, and the width of the sketch, the number of columns. So basically, Countman Sketch allows me to remember various identifiers, maybe video IDs for our problem. And then we can query those identifiers and then retrieve an approximation, actually an upper bound on the count that it has been added to the sketch. Okay, cool. We've got Countman Sketch. It allows us to keep track and remember the counts of things. But how do we query the sketch for the top K items? We can't actually just go to the sketch values and then divine what items were in it. In some sense, the sketch forgets the identifiers. It just remembers their imprints. And so we have to be clever and pair this sketch with something more traditional, like a sorted list. So a typical process would be like this. When a view comes in, we will add the count to the sketch for that identifier. That will increment all of those indexes so that way we can query them later. We are immediately after we add, we're going to query the sketch for the approximate count for that item. Because at that moment, we remember the identifier. That thing did get a view at that moment. And so it is a potential candidate for our top K. So we're going to query its value and return that here. So maybe we have video 1 has actually been seen 1,000 times now. At that point, we will go and update a sorted list or a heap. And the idea is this sorted list doesn't need to be all 4 billion videos. This might be just a few thousand videos. But in general, what we're expecting is that this sorted list will get updated every time something important happens. And so the sorted list, we can basically restrict those updates to only view counts that are greater than the bottom of the list. We don't really care about view counts on items that are way below the top K. They don't matter to us until they reach that threshold where they're actually in the running for the top K. So in practice, what you might do is you might use something like Redis for this. Redis has 2 data structures. It has native support for Countman Sketch. So you would use the cms.incrby in order to add, I think it has a query command. I forget exactly what it's named. And then each view, the view consumer would grab the ID, it would increment, it would read that value, then it would check to see if it was greater than the lowest number in the sorted set. And then it would add that item or update that item into the sorted set. When our users come in and they want to query the top K, they'll go to the Redis cache, they will query those values, and they will return them back to the user. Now, of course, using a volatile store like Redis for this, we have data loss potential. So you would want to consider how you maintain replicas, how you use append-only file, and other pieces there. This gets a little bit hairy because when we add an item to Redis cache, if Redis cache crashes and we have to restore it, it's difficult for us to know whether that item was added in what we have in our backup, basically what we can restore from the append-only file. But remember, this is an approximation. So like if the system introduces some error, it's not mathematically optimal, but it's probably not breaking the bank in terms of the outputs to our users. Remember, they may not be able to validate this. Now, another option for us is to put the Countman sketch inside of Flink. Basically, we would have the sketch be part of the state that Flink manages. It would checkpoint that state and keep it externally. The sorted sets and heap would basically be in memory. They would be persisted durably so that they can recover, but this would actually be probably a more rugged option for us. And then periodically, Flink would flush that out to something like Redis so that it could be read by our top K service and returned via an API gateway. Again, the Flink solution here kind of feels hand-wavy, right? Interviewers are going to want to go into a lot more detail about that, but it has this nice property of doing this all in memory. And that means it can be lightning fast. Like if our goal is to minimize the amount of hardware that we use for this problem, that is probably one of the best solutions that we could employ. Now, so far, we've talked about what this looks like for tumbling windows where we're only adding. I want to make a couple notes here. Countman Sketch, if you go read the Wikipedia page, you're going to see that you can add and query. There's no subtract operation. And that's partly true. If you have what are called turnstile operations where you are only removing things that you had previously added, then you can guarantee a lot of the same properties. If you look on the article, we have some links to references that explain what this looks like. And so if you wanted to do this with a sliding window, you would do much the same thing that we did earlier. You would basically add views as they happen, and then you would remove them 60 minutes later or 1 month later. You could do that by having a separate consumer group that reads off of the Kafka topic, or you could potentially have Flink retain all of that in state. That seems a little bit duplicative, but you would basically add and remove items so that the sketch represents the sliding window. And then the sorted list or heap needs to be sized accordingly. We need to have some buffer, so that way items that are low and then might be gaining into the top K, when other items fall out of the top K, as in they are decremented. But you might use a sorted list or a heap of size like 5,000, and you're likely going to cover all of the scenarios that you might care about. Of course, there is mathematically a scenario where 5,000 isn't enough. But remember, this is also an approximation. So we kind of don't care about those situations that A, are never going to happen, but B, only affect our result in these very edge case scenarios. So this would be an example of a highly optimized approximate system. I think if interviewers are looking for this solution, they're basically looking for whether you've studied this problem before. And I don't think it's a particularly good interview question. So if you get one where the interviewer was expecting this, I apologize. I think it's esoteric, but I hope that this was interesting for you as you think about how you might design systems at even higher scale. I would not probably recommend starting with an approximate solution in an arbitrary interview for the one risk that the interviewer may not actually understand a lot of what we're talking about here. That is a real risk that we've seen from some of our users in comments where their interviewers just don't quite get it. And it can happen. So be careful and try to veer toward simpler, more proven solutions like we talked about earlier on in this video. Before we wrap up, I wanted to give some commentary on some specialized databases that people are commonly asking about for these problems. The specialized databases have some downsides that I think make them disfavorable for using in an interview setting. The worst case scenario is your interviewer is just not familiar with the technology that you're bringing to the table. And they've got two options there. Either A, they say, use something else. I pretend like that doesn't exist, in which case all of your knowledge goes out the window, or they ask you to explain it at a much finer granularity. They basically want you to explain the internals of whatever database you're using. In which case, if you've got that knowledge and you've been working with it for a while, fantastic. But a lot of times that's going to sound a lot like the general solutions that we've been talking about, where instead of talking about hypertables and continuous aggregates in timescale, we're talking about how we do pre-aggregation and then how we query it from our database. It's just easier in most cases for you, if you're preparing for interviews, to think about solutions that work with simpler technology stacks than ones that work with very specialized technology. And I know somebody in the comments will say, no, none of this is very specialized. Agree to disagree. In terms of the options here, I've got a few opinions. Timescale is an extension on Postgres. They basically take the table metaphor and they call it hypertables. They're basically tables with time series, which is more efficient for both storing and retrieving time series data. And then they add some additional capabilities on top of that, like continuous aggregates. The continuous aggregates basically generates new tables with aggregated data as the data is coming in, which is really cool for our purposes because those generated tables can have indexes on them, which means that we can have continuous aggregates for our tumbling windows with indexes on the aggregate views, so we can make the querying really efficient. In some sense, this being built on Postgres saves it from the problems that other time series databases might have. Now, in the more strict time series database, we've got Prometheus. Did I spell that right? Yeah, in InfluxDB. Prometheus is used in a lot of observability stacks. If you use Datadog or New Relic or Grafana, you've probably either used Prometheus directly or use something like it. These are specialized and they're intended to basically support a single screen graph. It's like we want data points over time for one series. And the capabilities there are really good. You can upsample and downsample. The problem comes when you want to look across screens, across graphs, across series, or in Prometheus language, across labels. If we want to do a top K query, we want to go and take all of the series for each of the videos, and then we want to sort them. And these databases aren't going to help us out at all in that process. So we're going to have to query the database 1 billion times for each of the series and then sort it externally. And at that point, you're kind of like, well, what is this doing for me? There are probably some, I think, suboptimal solutions using some of the techniques that we talked about earlier, where you can cache or, run some pre-processing. But in general, I don't think they fit this problem quite as elegantly as some of the alternatives. So I would shy away from using these. The final category are what I would call like real-time OLAP or streaming OLAP solutions, Druid, Pinot, ClickHouse. Generally speaking, these are going to provide some variant of materialized views that allow us to do that aggregation internal to the database. So like Flink has subsumed a lot of the challenges of streaming frameworks around checkpointing and state management, these OLAP databases have subsumed a lot of the problems that are associated with streaming analytics use cases. That is both good and bad. It's a blessing and a curse for this problem in that it's kind of makes it trivial. It's just a configuration that you would have on some of the input. And as a result, there's just not a whole lot to talk about in an interview setting. It's also very likely that your interviewer is not familiar with all three, maybe even some of them. So, same caveats apply. If I was preparing from scratch, I would not spend a lot of time trying to memorize or understand some of these more specialized databases or frameworks. Instead, I would invest my time in really trying to understand data flows, some of the core patterns around aggregation, caching, etc. And then what you'll find is that those things are going to basically be implemented in some of these technologies. You'll give yourself a leg up in understanding why the tech exists and then how it works under the covers, so that you're ready to go when the interview happens. All right, folks, we have covered a lot of ground in this breakdown. We've covered stream processing, approximation techniques, count-min sketch, time series databases, the works. I hope this was useful for you. I think if you're at the end of this video and you're going, wow, some of that was overwhelming, I want to let you know that, yeah, some of it was probably beyond what you'll need in an interview setting. So go back to some of those core deep dives if you're really looking to say, all right, what do I actually need to be ready? But I want to encourage you that understanding how data flows through a system is the unlock for infra-style interviews. And if you can get a handle on how big are the tables and where are they flowing and when is the compute happening sooner or later and what does the caching look like, you're going to be able to solve a lot more problems than if you just try to memorize solutions and parrot them out in an interview setting. Please hit up the comments if you've got questions or suggestions. The article that we have linked will probably have more up-to-date updates as we go, just because the video will be fixed. But we really appreciate your time and hope this was useful. Till next time.